There's a machine on the market right now that pulls drinking water directly out of thin air. No plumbing, no well, no connection to any water source at all. Just air going in and clean water coming out. It costs $2,000 and runs on electricity around the clock. An Australian engineering student named Edward Lineker won the James Dyson Award in 2011 for building the exact same thing in his mother's backyard for the cost of a trip to the hardware store. His version had no electricity, no compressor, no moving parts, and produced a liter of water a day in drought conditions. And the principle he used to build it was not new, it was not modern, it was not even his idea. Persian engineers figured it out in 500 BC and built versions of it that are still producing water in Iran today. Stick with me, because I am going to show you exactly what this system is, how the ancient version worked, why it still works, and how you can build a functional version of it yourself for under $50 using materials from any hardware store. The industry does not want you thinking about this. Commercial atmospheric water generators have been a growing market for years, $2 billion globally and climbing. The selling point is that water is everywhere in the air around you, even in a desert, and with the right technology you can pull it out. That part is completely true. Even the driest air contains 11.5 milliliters of water per cubic meter. The part the industry does not advertise is that you do not need a compressor, a refrigerant loop, or a power supply to access it. You need a temperature difference. And the ground beneath your feet has been providing that temperature difference for free every single day since the Earth formed. Here's the physics, and it is simpler than it sounds. Warm air holds water vapor in suspension. The warmer the air, the more it can hold. When that warm air is cooled down past a specific temperature, the dew point, it can no longer hold all the vapor it is carrying, and that vapor condenses into liquid water. This is exactly what happens on the outside of a cold glass on a humid day. The glass is below the dew point of the surrounding air. Water appears on the surface from nothing. The air gave it up. The question is, how do you cool air without electricity? The answer is the same answer Persian engineers arrived at in the first millennium before the Common Era. You put it underground, soil temperature at 2 meters below the surface stays relatively constant year-round, typically between 6 and 15 degrees Celsius depending on your region, while surface air in summer can be 30, 40, even 50 degrees. You draw hot surface air down into the cool earth, and the air gives up its moisture as it cools. You collect that moisture. You have water. No power required, no refrigerant, no moving parts beyond the air itself. The Persian system that used this principle was called a qanat, an underground network of tunnels and channels hand-dug over centuries that moved water from highland aquifers to the lowlands by gravity. Qanat technology is believed to have originated in Persia in the early 1st millennium BC, and today there are an estimated 50,000 qanats in Iran alone, 3/4 of which are still working. They are not curiosities. They are active water infrastructure, older than most civilizations, still standing, maintained by communities who have never needed an electric pump because the system does not require one. The air from a qanat is drawn into the tunnel and cooled both by contact with the cool tunnel walls and by the transfer of heat as water evaporates into the airstream. In dry desert climates, this can result in a greater than 15 degrees Celsius reduction in air temperature, producing cool, dry, comfortable air from conditions that are anything but. Edward Lineker took that exact principle in 2011 and applied it to a simple backyard prototype. His airdrop design pulls warm surface air underground through a network of copper piping, cools it to soil temperature, and harvests the condensate water into an underground collection tank, producing about a liter of water a day in the drought conditions of southeastern Australia. He won the world's most prestigious design award for it. The principle was 2,500 years old. The materials were available at any hardware store. Here is how to build a functional version yourself. The real prices, the real materials, the real yield, no inflation. You need 4 things: a length of copper pipe or coil. Copper is important, not PVC, because its high thermal conductivity allows it to transfer the temperature of the surrounding soil into the air, moving through it as efficiently as possible. A 10-foot coil of half-inch soft copper refrigeration tubing runs approximately $25 to $35 at any plumbing supply or hardware store. A food-grade unspettinas 5-gallon bucket with a lid, $4 to $7 at any hardware store. A length of PVC pipe for the surface intake, 2 to 3 feet, under $5, and basic fittings to connect them, another $5. Total materials, $40 to $50, not $15, and I am telling you that up front because you deserve the real number. Here is how it goes together. Dig a hole approximately 2 feet wide and 2 feet deep. Deeper is better if your ground allows it, because the further you go down, the more stable and cool the soil temperature. The bottom of the hole is where your copper coil lives. Coil the copper tubing in a loose spiral inside the bottom of the hole. The The more surface area the coil has in contact with the cool soil, the better the heat exchange and the more water you collect. Run the two ends of the copper coil up and out of the hole. One end connects via PVC pipe to a surface intake that rises above ground. This is where warm surface air enters the system. The other end terminates inside the food-grade bucket, which sits at the bottom of the hole alongside the coil. That bucket is your collection reservoir. Drill a small hole in the bucket lid to accept the copper pipe end. The lid keeps collected water clean and prevents evaporation losses. Backfill the hole around the coil and bucket, leaving only the PVC intake pipe exposed above ground. Warm surface air enters the intake. It travels down through the PVC into the copper coil, where it sheds heat into the surrounding cool soil. As it cools past its dew point, water vapor condenses on the inside walls of the copper tubing and drips down into the collection bucket below. You pull the bucket out of the ground to harvest the water. Rinse and repeat every morning. The yield depends on two things you cannot fully control: the humidity of your local air and the temperature differential between the surface and your soil at depth. Published research confirms that passive systems in arid and semi-arid regions yield between 0.3 and 0.6 liters per square meter of condensing surface per day. A 10-foot copper coil gives you roughly half a square meter of internal surface area. In a humid climate in summer, you can realistically expect between 0.3 and 1 liter per day from this setup. In a true desert with very dry air, less. This is not a primary water supply for a family. It is an emergency backup, a survival system, a garden irrigation supplement, or, and this is the most important framing, proof of concept that costs $50 instead of $2,000. Build 2 or 3 and you triple the yield. The copper coil is the limiting factor on surface area. More coil, more water. 2 practical improvements that meaningfully increase yield for almost no additional cost. First, insulate the PVC intake pipe above ground with black foam pipe insulation. $4 at any hardware store. Black absorbs solar heat during the day, warming the incoming air above ambient temperature before it enters the underground coil. The greater the temperature difference between incoming air and soil temperature, the more condensation you get. Second, line the inside of the intake pipe with copper wool or steel wool. This increases the surface area that the air contacts as it cools, giving vapor more opportunities to condense before the air reaches the collection bucket. Edward Lineker specifically documented using copper wool inside his tubing for exactly this reason. One important note before you go: the water collected by this system is condensate, essentially distilled water produced by condensation, similar in purity to rainwater. It is free from minerals and most contaminants that come from groundwater. However, it picks up whatever is in the air and on the surface of your copper pipe. So running it through a basic activated carbon filter before drinking is a sensible step and adds $3 to $5 to the setup using a simple inline filter cartridge. The water is not potable straight from the pipe in the same way that water from a tested municipal supply is. Filter it first. The atmospheric water generation industry sells you a compressor, a refrigerant loop, a filter system, and a $2,000 enclosure to do what a copper coil buried 2 feet in the ground and a $5 bucket does through the same fundamental physics. The Persians built it with hand tools and clay. An engineering student built it in a backyard and won an international award. The ground beneath your feet is cooler than the air above it every single summer day. That temperature difference is the machine. It has always been there. You just needed to put a copper coil in it. Share this with someone who is paying for bottled water and has a backyard, because they're sitting on the solution.